Hello, pre-calc students. This is Mr. Beck, and today I'm going to talk you through our lesson on 2.6. 2.6 is all about building models and applications of mathematics in the real world. So that question you've always been asking, where are we going to use this in real life? Well, now is that opportunity. We're finally getting it answered. And I know you're so excited about that. So join me in your excitement as we talk about 2.6. What 2.6 is we're going to take situations, and a lot of times situations in the real world really depend on not just one variable, but multiple variables. One of the big cases of that is, let's talk a rectangle. A rectangle has a length and width. Let's just call that the length, let's call that the width. So our rectangle having a length and width, suppose we wanted our perimeter. Our perimeter is based off of both the length and the width. And to do any work with the perimeter, we need to know both. Now, what happens if your perimeter is set, it's a fixed number, then the length and the width kind of work together in tandem to come up with, how do these fit into the parameter of a set perimeter. Perimeter. Did not mean to say that, but okay. Anyway, the whole purpose of this is to say many times we have codependent variables in our situation. These codependent variables, one's not really independent of the other, but the two have to work together in tandem to fit the overall situation. So with that said, we're going to work with our cases where we have these codependent variables, but it makes life easier if we can base these variables or base our overall situation off of a single variable, meaning that I want to come up with a function of just one variable so that if I change the one variable, I know what happens. So if the length gets changed, I already know that the width is kind of built into that function. So let's jump into the problem so you can see exactly what I'm talking about. So the very first problem I have is the width of a rectangle is 3 more than twice the length x, where x is in centimeters. Our goal is to, first of all, write the formula for the area of a rectangle. So the area of a rectangle, as you see here, is length times width. You guys should know that really, really well. So not an issue for most people. The area is length times width. Now, what I want, and this is where we're going to jump in to what we're doing today, we want to write the area as a function of x. So as x changes, how does the area change? Now, first of all, what does x represent? X represents the length, and that's stated here in the problem. So x is represented by the length. And then, so that's our primary equation. We want to come up with a secondary equation. The secondary equation really takes that codependent variable and puts it in terms of the other. So really, it's the equation that puts everything just based off of that singular variable x. And we have that here when we say the width is 3 more than twice the length. I know addition's commutative, but please make sure that if you see 3 more than, you always do it as plus 3, because 3 less than is minus 3. So order of addition doesn't really matter, but it's also like proper just mathematics to write it and set it up that way so that there's not any kind of issues later on when commutativity does not work. So moving on. If we have our width based off of x, which is what that 2x plus 3 is, we have our length based off of x, we now can find our overall area based off of x, which we simplify into 2x squared plus 3x. So a of 1 and a of 2, those are pretty easy to calculate. A of 1 is going to be 2 times 1 squared plus 3 times 1, which is 5. A of 2 is 2 times 2 squared plus 3 times 2, which is 14. Now, that's great. That's some easy math that we're doing. But the more important thing is explain what this means. And I'm saying this because getting yourself into the problem and understanding what all the x's and the y's represent help you understand so much more about why we care about the mathematics behind it, really. So when the length is 1 centimeter, and please keep units in mind, the area of the rectangle is 5 centimeters squared. How do we know it's centimeters squared? Well, we are told that x is in centimeters up here. So if our x is in centimeters and our width is based off of centimeters also, it's also in centimeters, so centimeters times centimeters. So when the area is, or when the length is 2, the area is going to be 14 centimeters squared. Now this next question, what is the implied domain of a of x? Now to do this, what I'm going to do is I'm going to open up Desmos, and I already have these pre-designed for you, but We have this Desnos graph of a of x equals 2x squared plus 3x. Now, the domain of this parabola is all real numbers, and we can see that because length goes from negative infinity to positive infinity. So the domain is all real numbers. However, what's the implied domain? And this is going to be the big difference. The implied domain is what x's truly fit the situation. Well, the x's that fit the situation, what does x represent again? X represents the length of the rectangle. Lengths are not allowed to be negative numbers. So what that means is this graph really should only look like this, where we're seeing from 0 to infinity. So the implied domain, gonna pause this while my technology catches up with me. All right, I'm back. Sorry about that. Technology just had to catch up. So the implied domain, as I was saying, is instead of all x is such that x is greater than 0, once again, because length is not allowed to be a negative. Our second problem, we should let P be a point on the graph of y equals x squared minus 2. So what I did here was, and let me erase these because we're going to be using that information. What I did was I graphed y equals x squared minus 2. And then I said, okay, P is a point on that graph. Let's represent P by a bright pink dot. So P is any point on the graph. So this could be P, where this is x comma y. This could be P, where this is x comma y. This up here could be P, where this is x comma y. So really, this P is a very movable point for you. And this kind of shows the flexibility of mathematics that we know that we have these variables as x comma y, but this is the codependency that really the x and the y kind of work together in tandem with each other to come up with the overall situation. So what is that situation? We want the distance d, so the distance d from the point P, which I have a variety of point P's on there, so any of these point P's, to a point that's given. And the point that's given here is the coordinate -1, 3. So let's go ahead on this graph. Let's plot -1, 3. Everybody sees that right there. And so what we want to establish is a formula, distance from any point on the parabola to that point as a function of x. So what is this distance as a function of x? What is this distance as a function of x? What is this distance as a function of x? Pretend that's straight. So that's what we want. We want all these distances as functions of x. So that means distance, distance. Hey, let's use the distance formula, which is what I have here. So this distance formula is honestly based off of 4 variables, x1, x2, y1, and y2. So we can substitute the point that we have in here. Let me go ahead and highlight. We could substitute that point and the generic point xy in for x1, x2, x1, and y1. Now, y2 is actually this coordinate of x squared minus 2. We can see that a little better because the y, knowing this relationship, we can write that y coordinate as x squared minus 2. So this is our secondary equation here. They gave it to us in an equation. And oftentimes this is going to happen that if we have a point on the graph, the secondary equation is the graph that's given, or is the equation that's given. So now here I have my distance as a function of x. I could simplify this. Simplified, I believe, let me change this to a blue color. Simplified version is going to be the square root of x to the 4th minus, have to do some mental math here, which, you know what, let's just not bother doing that. So, because I now have my distance as a function of x. If my distance, what's d of 0? D of 0 is the square root of 26. We could plug that in. 0 squared, so 0 plus 1 squared, and 0 minus 5 squared. So those are my d of 0, which is the square root of 26. What I would like to do is I'd like to show you what that represents. When the x value is 0, meaning this is the point that I have on my graph, what is the distance from that point to that point -1, 3? So if we use the distance formula or Pythagorean theorem, we could see that's 1 squared plus 5 squared, which is essentially what we have here, or the square root of 26. And then d of 1, D of 1 you have in green. So D of 1 is going to be the square root of 4 plus 16, which is the square root of 20. So the distance from here to here is the square root of 20. Now, this kind of leads me to wonder, okay, so this is the square root of 26, this is the square root of 20, so this distance is getting smaller. So the distance will continue to get smaller up until like right about here, and then my distance is going to start getting bigger and bigger and bigger again. So that question is, what gives us the smallest distance? So what x value gives us the smallest distance? And this is where we are going to turn to Desmos again. So let's open up Desmos, turn off that graph, and let's put on this graph, which I have. So this is the graph of what exactly? So the y-coordinate of this graph is distance. The x-coordinate of this graph goes back to the parabola I had there before. So the x value represents the x-coordinate of the parabola. The y value on this graph is represented by the d, or the distance. The nice thing about Desmos is when I touch the graph, all of my local extrema come up as well as the absolute extrema if it exists. So my question became, where did I have my smallest value? So because I can't really show and like draw on this part of the app. So this is where I said, okay, my distance was getting smaller and smaller and then suddenly started getting bigger again. But the smallest distance really occurs when x is negative, specifically negative 2.175. So when the x value is negative 2.175, the distance to that, or from negative 1,3 to that point is 1.205. So going back to this graph, we said when x was negative 2.175, I believe it was, the distance to that point is going to be the absolute smallest. And just fun geometry fact, this is where we are perpendicular to the parabola. I love throwing in those random math facts where I can just because it helps connect the mathematics. And that's what this is all about, connecting the math together. So, and that's what I use to answer part C. Now, question number 3, and this is what we haven't talked about yet at all. A piece of cardboard measuring 10 inches by 13 inches is going to be used to make a box. So this piece of cardboard I have drawn out here is 10 by 13. Now, this box is going to be made by cutting out equal squares from each corner. So I tried to show that here by I'm taking off that square, that square, that square, that square. And when I do that, it folds into this box here. And I've seen this in action. I think it was at Papa John's when I was in college. They had all of their cardboard boxes that they used to make their overall boxes. So they were just flat cardboards, and then they folded it up to make an entire box. Yay, so real life application. Anyway, what's my goal? Write an equation that would calculate the volume of the box as a function of x. So let's talk primary equation. This is my primary equation. What is the volume of a box? Volume of a box is length times width times height. All right, we got that set. Now, how do we get it as a function of x? Well, what does x represent? In the problem, it tells us x is the height of the box. So this x and this x makes sense. So if x is the height of the box, what I have drawn out for you, I have this pink portion of the box. Its length is really 13. I guess it's pinkish. 13 minus 2x because we have cut this x out and this x out. And then this length right here is going to be 10 minus 2x because we have cut this length out and this length out. So with all that said, I now can establish that the length is 13 minus 2x and the width is 10 minus 2x. So now I can put that all together and make this as a function of x. And by the way, this is the one that I was thinking about that I'd already multiplied through at least once. Wasn't the other problem. So moving on, I now have my volume as a function of x, and this is the simplified version. So v of 1, I have said, is 88. If we plug in 1, 4 times 1 minus 46 times 1 plus 130 times 1 is 88. Okay, so far so good. What does this mean? Why do we care? So when the box height is 1 inch, then the volume is 88 cubic inches. And that's what we care about. So let's go back to Desmos because I already do have this graph. It's not that one, it would be this one. And this is kind of hard to see, so I'm going to go ahead and stretch the graph out just a little bit more so that we could see this in a little bit more context. So this is the graph of the cubic function. Hopefully you knew that it looks something like that. And the question that we're asked is, what is the implied domain of this problem? Okay, what's the implied domain in this problem? So there's y value, and I'm kind of bad that I didn't actually write it as v of x. Let me go ahead and correct that. So v of x is this. So 10 minus 2x times 13 minus 2x times x. So what is the implied domain? Well, a lot of people would say, okay, it would go from this x-intercept to this x-intercept because volume is not allowed to be a negative number. Most people are correct on that one. The volume is not allowed to be a negative number. However, that means that we're including everything from 6.5 on. Well, what is the implied domain? What does x represent one more time? So what does x represent one more time? X represents the height of the box. Let's assume that the height of the box is 7. If x is 7, we've cut out 7 inches from this side, 7 inches from this side. What that means is we've really cut out 14 inches from a side length of 13. Is that really possible? No, it is not. So the implied domain really is only going to be, and I'll stretch the graph, the implied domain is really only going to be this portion of the graph because that's the only thing that makes sense in the context of what we're doing. So naturally, that question comes out, what is the maximum volume? That maximum volume, is that the x, is that the y, is that, what do we do with it? Well, go back to the equation. The equation is v of x equals, which means our y value represents volume. And if our y value represents volume, the largest volume we can have is 108.399 cubic inches. And that's what I have here, 108.399 cubic inches. Our next problem, a rectangle has one corner on the graph of y equals the square root of 16 minus x squared. Big question, what does the square root of 16 minus x squared look like? And a lot of people wonder and they're like, I really have no clue. I've never seen anything like that before. Well, let's take a closer look at this. If I solve this, I square both sides, I get y squared equals 16 minus x squared. So x squared plus y squared equals 16. What this means is this represents a semicircle. So this is the equation of a semicircle. If you didn't know that before, well, you'll know it now. So there's my semicircle, or at least doesn't really look too much like a semicircle to me, but let's pretend. So it looks more like an oval, but moving on. So a rectangle has one corner in quadrant 1. So that's what I have in green here as the coordinate x, y. Now, another at the origin, which would be right here. A third on the positive y-axis, which I'm calling 0, y, which means that length is y. And then this on the positive x-axis is x, 0, so that distance is x, which sort of matches up with this generic point x, y that we have here on the graph. Now, kind of going back to what we did in one of those previous problems, since we know y equals already, can't we just call this x, the square root of 16 minus x squared? Yay, all right. So now, what's the area of the rectangle as a function of x? Well, going again, primary equation, area is x times y. Our secondary equation is that square root of 16 minus x squared, so we can put it together, area as a function of x. Now, what's the domain of A? We could really see that here. Our domain of A is based off of x, and x is only a positive value. Now, what happens if x is over here? We have no rectangle. So x has to be from 0 to 4. And so this is what the graph from Desmos looks like. Let's turn that off. Let's put that on. So our graph from Desmos, I'm going to have to stretch it out one more time. So where do we have our, and by the way, we could see our implied domain right here on this portion of the graph. Remember, the y value here represents the area. I could not call this A since I've already predefined a function A. But this is the area of the rectangle based off of X. So what's the largest area? The largest area is going to be 8. Where does it occur? When X equals 2.828. All right, so not too bad. Now, one of the things that I will point out, one of the homework problems that I have given you is going to be something similar to this, but the problem that's similar says we're not just working in the first quadrant. What happens if we work in the second quadrant as well? And if that's the case, everybody, this is going to be X. So this entire side length is 2X. Yes, please, please, please be careful about this. So the problem that's on the page right now is just quadrant 1, but you have a homework problem that talks about that being in quadrant 2 also. So first level 4 problem, and this one's kind of a tough one, especially for students to look at when they've never seen anything like it before, and I get that completely. What I did, just so you know, I did get a little bit more specific with my notes, and I said X is going to be the side length of the square. So it makes some of the calculations a little bit better. So what we have here is we have a wire that's 10 meters long cut into 2 pieces. So what I have here is represented by my 10-meter wire. When I cut it into 2 pieces, one piece gets formed in the shape of a square. Now that length I'm calling 4x because x represents the side length of the square. The other piece is shaped like a circle. So this 10 minus 4x ends up being the circumference of the circle. And that circumference is going to be kind of important here in just a moment. So if my goal is to find the total area of the 2 figures, first I need to know what's the area of the square. Well, because x is defined as the side length of the square, the area of the square is x squared. Yay, that one's easy. Well, this next one is not quite so easy. The reason why it's not quite so easy has to do with the fact that we have the circumference of this circle. The circumference of the circle is 2 pi r, but the area of a circle is pi r squared. So this is our secondary equation, if you will, that first we have to remember that circumference is 2 pi r. We can solve this for r so that now we know what the radius is. So we have our radius based off of x. And with our radius based off of x, then we can substitute that in for r right here. This is my r. And so my area is going to be x squared plus pi r squared, or x squared plus pi times that expression squared. Ugly, yes, I know, but at the same time, it is kind of usable still. So let's go back to Desmos. And this is going to be the graph of, I believe that 10 minus 4x over 2 pi, that whole quantity needs to be squared. So let's go ahead and fix that. Now we have a situation that looks like this, which means I'm going to have to change some of my things. 0.78, 0.721, and 1.803. 0.721 and 1.803. So 0.721 and 1.803. So there's our answer. The value of x that minimizes this is 0.721. Last but not least, we're in a boat 2 miles from the nearest point on the coast. So here's my beautiful picture. Your goal is to go to point Q. You are here. Now Q is 12 miles down the coast. So this distance right here is 12. All right. Now we are told, excuse me, that Q is 1 mile inland, and we are 2 miles from the coast. Just setting up our overall situation here for you. Talking too much. So, we row at 3 miles an hour. We walk at 5 miles an hour. So our first question: express the distance rowing as a function of x. So we find r of x, and to find r of x, r represents this distance right here. To do that, we have Pythagorean theorem, the square root of x squared plus x squared, or we could write as the square root of x squared plus 4. Square root of x squared plus 4. Our distance walking is going to be this distance right here. Once again, Pythagorean theorem, the square root of one side squared plus that. Now, I kind of jumped the gun and said, let's define this as what our x value is. If we define that as x, this is 12 minus x. We very, very well could have defined, and I'm changing colors here, we could have defined this as x, and this is 12 minus x. How do we know which way to define it? Since we're not told anything, I just picked a direction and went with it. So our distance walking ends up giving us this expression. Yes, I had to multiply that all the way through, 12 minus x squared plus 1. Now, this is the tough part. Express the total time of the trip as a function of x. To express the time of our trip as a function of x, we have to know something about what is time. Time, I'm given x, and x represents distance. So if x represents distance, and I need this based off of time, do I have a relationship between distance and time? This is where we are expected to know that distance is rate times time. So to come up with a time expression, we are going to take distance divided by rate. We're fortunate that right from the beginning, we are told different rates. Yay! So we're going to break this up into our time total is going to be the time rowing plus the time walking. So that time rowing is going to be distance rowing over rate rowing. And every time I say rate rowing, I think of Scooby-Doo. I apologize. But distance rowing over rate rowing plus distance walking over rate walking. And those distances that we had before are, the reason why I set it up this way is so that we could just break down how we set up each of the individual problems. So distance over 3, because that's our rate rowing, plus distance over 5, because that's our rate walking. That's a pretty fast walker, by the way. So what's the domain of t? T is based off of x, so t is a function of x. What does x represent? X represents this distance to a random point on the shore. So that distance has to be between 0 and 12. If x ends up being a point over here, then all of a sudden we don't really have this triangular situation that works out. If x is over here, then we don't have this pinkish triangle that I have over here. So x has to be a number between 0 and 12. Now notice how I included both 0 and 12 here, because what if we wanted to go straight down? If we go straight down, that's possible, or we can end up at that exact point also. So moving along. How long will it take you to travel to Q if you land the boat 4 miles down the coast from point Q? Uh-oh. I probably should have defined this the other way, where I probably should have defined that as x and the other one is 12 minus x. It's too late now. I have all my calculations built in and done already, so I'm not going to stress about it. We just have to think through it. If this distance is 4, that means that x has to be 8. So that means that I want to find t of 8. And t of 8, using Desmos, t of 8, you can see here I have is 3.573. And what's our minimum? And this is where Desmos is great. All you have to do is touch the graph, and then our absolute minimum is going to show up. That is 1.49. That's what x represents. So when you go 1.49 miles down the coast, let's actually draw that back out. So when you go 1.49 miles down the coast, then we get our minimum time. And it doesn't ask us for that minimum time, but I wrote it down here for you. So hopefully you appreciated the notes and you understand, and I look forward to working with you next week.